Usually when we talk about deploying software, there is this comforting expectation of a pipeline.
Right, yeah, like a totally linear sequence.
Exactly. It operates like a vending machine. You put your code in at the top, press a button that says deploy, and the gears just turn in this highly predictable mechanical sequence. And then, your application just drops out the bottom.
Yeah, a shell script runs, it finishes, and you're just done.
Right. And as engineers, we love that predictability.
Yeah.
We really like our systems to run like a script. But then you step into the world of Kubernetes, and suddenly you realize that someone has completely dismantled your vending machine.
Yeah, totally dismantled it.
We're looking at an orchestration landscape that, honestly, it feels more like a chaotic bulletin board in a busy office. Yeah. There's just no central script running the show.
And that realization, that is the absolute definition of a distributed control problem, because whenever the system feels complicated or, opaque to people, it usually means you're trying to understand it as that linear pipeline, which it fundamentally isn't.
It's not a script.
No, not at all. To really grasp what's happening under the hood, we have to establish one core premise, like a guiding rule for this entire deep dive today. And that rule is, Kubernetes stores intent, it observes reality, and it continuously acts to close the gap between the two.
Stores intent, observes reality, and continuously closes the gap. I love that, because it immediately shifts your mindset away from running commands. And today we have a very specific mission for you, the listener. We are going to transform Kubernetes from this confusing cloud of buzzwords where you just memorize a diagram of 50 disconnected boxes into a clear, predictable, mechanistic mental model.
Yeah, we're definitely not doing a vocabulary test today.
Definitely not. We're building a reasoning model.
Precisely. We need to look at the physical mechanisms. And to make this concrete, we have a central storyline for this journey. We are going to trace one single action. Imagine you're sitting at your terminal and you type kubectl and apply -f deployment.yaml. You hit enter.
The classic command.
Right. We are going to follow that specific request microscopically, step by step, code path by code path, until a Linux process is actually running, healthy, and receiving network traffic.
And as we encounter different architectural components along this journey, we're going to use a specific learning framework. Instead of just memorizing what a component is called, we want you to ask 5 mechanistic questions about it.
Okay, what are they?
First, who writes to it? Second, who watches it? Third, what side effect is supposed to happen? Fourth, what status field should change to reflect that effect? And finally, what physical reality can prevent convergence?
That's a great framework. So before we can orchestrate thousands of containers across, a fleet of machines, we really have to start at the absolute lowest level. We need to understand what a container actually is. Because, and spoiler alert here, Kubernetes itself does not actually execute your application code.
Wait, yeah, that is a massive misconception. People think Kubernetes is this hypervisor that magically spins up virtual machines or containers.
Yeah, they treat it like magic.
But at the lowest useful level, a node in your cluster is just a regular Linux server. It's just running Linux processes. And a container isn't a magical physical box. A container is literally just a standard Linux process or a group of processes that has been started with a deliberately constructed view of the machine and a deliberately constrained share of resources.
Exactly. The Linux kernel, not Kubernetes, is what actually enforces those boundaries.
Right. And this is where we need to look at the exact kernel mechanisms. Because the source material breaks down how we create this illusion using 2 main Linux kernel features, namespaces and C groups.
Let's start with namespaces. The mental framework here is that namespaces divide visibility. They answer the question, what can this process see?
Right, because normally if you just run a close on a Linux box, you see every process running on the system. You see the whole file system tree. So how do we trick a process into thinking it's completely alone? We use namespaces.
Yeah, and there are several distinct families of namespaces that we sort of stitch together. Let's look at the PID namespace first. This gives the process a completely private process tree.
Right, so when the container runtime starts your application, it uses a system call called clone.
Yep, clone.
And it passes specific flags to create a new PID namespace. So inside the container, your web server application might query the kernel, and the kernel tells it, hey, you are PID1. It thinks it's the absolute root process of the machine.
But on the host node, if you look at the master process tree, that exact same application is actually running as PID 4592. The kernel is just lying to it.
It's just maintaining 2 separate translation tables for process IDs. It's amazing. And there is the network namespace.
Yeah.
This is crucial because it gives the process its own entirely isolated network stack. It gets its own virtual network interfaces, its own routing tables, own IP addresses.
Right. If you run ifconfig inside this namespace, you do not see the host's eth.interface. You only see the interfaces that were explicitly moved into that specific namespace.
And then we have the mount namespace, which is, honestly, it's arguably the most complex one.
Oh, definitely.
It ensures the process sees a specific file system tree. It's like a vastly more powerful version of CRUD. It isolates the mount points so that when the process looks at the root directory, it only sees the files from the container image, not the underlying host operating system files.
And we also have the UTS namespace, which isolates host names. So the container thinks it has its own unique host name. Then there's the IPC namespace.
Inter-process communication, right?
Exactly. It isolates IPCs, so containers can't use shared memory to accidentally, talk to processes outside their namespace. And finally, the user namespace, which is a massive security feature.
Oh, I love this one. It maps user and group IDs between the container and the host.
Right. With user namespaces, your process can run as the root user inside the container with full permissions to install packages or modify files within that isolated mount namespace. But that root user is mathematically mapped to an unprivileged standard user ID on the host.
So if that process somehow breaks out of the container, it has absolutely no root privileges on the actual physical node.
Exactly. It's brilliant.
All of these namespaces together create this flawless illusion of an isolated operating system. So if namespaces divide visibility, the other half of the equation is groups, control groups. And our framework says C groups divide capacity. They answer the question, how much of the physical hardware can this process use?
Yes, and it is absolutely vital to understand that the kernel handles CPU and memory very differently under C groups. A CPU limit usually translates to a time-based throttling constraint, specifically using the completely fair scheduler, the CFS quota.
Let me explain how that actually works, because it trips people up constantly.
Yeah.
If you give a container a limit of half a CPU, the kernel doesn't just, dedicate half a physical core to it.
Right, it's not a spatial slice.
No. Instead, it measures CPU time in periods, usually 100 milliseconds. So a half CPU limit means your process is only allowed to execute on the processor for 50 milliseconds out of every 100 millisecond period. If it tries to execute for 51 milliseconds, the kernel suspends the process.
It doesn't crash it, though.
Right, it doesn't crash. It just goes to sleep until the next 100 millisecond window opens. It gets throttled.
Which means your application will simply experience high latency. It'll feel sluggish. But memory is a completely different beast. You cannot throttle memory. You can't just tell an application to pause its RAM usage.
Exactly. A memory limit is a hard physical boundary. If your crew group exceeds its memory limit and the kernel cannot reclaim any memory pages by swapping or dropping caches, the kernel invokes the OM killer, the out-of-memory killer.
Yeah, that's brutal.
It is. It finds the process inside that crew group that is using the most memory, and it sends it a SIG-kill signal. It terminates it instantly.
And this leads to a classic production trap. You can have a container get killed for reasons, even when the host node itself has 128 gigabytes of completely free RAM. The overall node is totally fine, but the specific process hit its localized tree group boundary.
Let me share a massive host trap here, actually. A war story that almost every Java developer runs into when they first move to containers. Let's say you have a Java application. You deploy it to a Kubernetes cluster, and you set a memory limit of 2 gigabytes. But your container keeps silently dying and restarting. You look at the logs, nothing.
Oh, I know exactly where this is going.
Right. Why does it happen? Because older versions of the Java virtual machine didn't understand tree groups. The JVM would boot up, look at the underlying host, see 128 gigabytes of total RAM, and say, great, I'm going to set my max heap size to 32 gigabytes.
Yeah, it thinks it owns the whole box.
Exactly. So it starts consuming memory, it hits the 2 gigabyte tree group limit, and the Linux kernel instantly executes it. The JVM never even got a chance to throw an out-of-memory exception in the logs because it was killed by the kernel from the outside.
That is exactly why understanding the underlying physical mechanism is so critical. The container doesn't know it's a container unless the runtime explicitly configures it to be aware.
Now I have to ask, if this is all just Linux kernel trickery, how can I actually prove this isn't just magic? If I'm sitting on a node, how do I peer behind the curtain and see the actual physical process?
You can absolutely prove it, and doing so is honestly the best way to build your mental model. If you have a pod running, the highest level way is using kubectl exec to run a command inside it, like kubectl exec your pod name psdef. You'll see your process running, likely as PID1, completely isolated.
But what if I want to see the truth from the host's perspective?
Then you SSH into the underlying Linux node itself. You can run node-level tools. You can run kubectl inspect to see the exact JSON configuration the runtime passed to the kernel. But my favorite way to prove it is using a tool called incenter.
Oh, and Center is fantastic.
It really is. This command allows you to take your current host shell and literally inject it into the namespaces of that running process. You can enter its network namespace and run ifconfig to see exactly what it sees.
Or from inside the container, you can simply run cat pro1c group. Instead of seeing generic container metadata, you will see the explicit host-level C group file paths that the kernel is using to restrict that process. It just rips the curtain right back.
Right. So we know what the kernel is doing, but Kubernetes itself isn't making these clone system calls, is it?
No, it delegates that.
Yes. There is an interface chain, and the boundaries here are strictly defined. Kubernetes runs a component on every node called the kubelet. And the kubelet does not talk to the kernel. The kubelet talks to an API called the Container Runtime Interface, or CRI.
The CRI is just a gRPC protocol. It's just a standard way for the kubelet to say, hey, run this image.
Exactly. The CRI talks to a high-level runtime, something like containered, or CRIO. These high-level runtimes manage the images, pull them from the registry, unpack them onto the disk, and manage the API requests. But even container doesn't talk to the kernel directly.
Right, it delegates again.
Yes, it delegates to a low-level OCI runtime, the Open Container Initiative runtime. The most common one is called runc. And runc is just a small command line tool whose sole purpose in the universe is to take a JSON specification, make the raw system calls to the Linux kernel to set up the namespaces and T-groups, start the process, and then exit.
So the chain of command is basically Kubernetes delegates to the kubelet delegates to container delet, and container delegates to runc, which actually asks the kernel for what it wants. We don't embed Docker, we just use this standardized chain of command.
Precisely. And this modularity is why you can swap out container for something like Kata containers, which uses lightweight virtual machines instead of namespaces, and Kubernetes doesn't even notice the difference.
Wow. Okay, so we've exhaustively established what one isolated process is at the lowest level. But let's be honest, starting one container manually with runc is relatively easy. The real problem is, what happens when we need to keep 5,000 of these processes running across 200 unreliable virtual machines?
Yeah, that's the real challenge.
A node kernel panics, a network switch dies, a data center loses power. This introduces the absolute need for a distributed control system.
And this is exactly why Kubernetes exists. Operating highly dynamic containers across fundamentally unreliable physical infrastructure is a coordination problem. And Kubernetes solves this coordination problem by exposing a purely declarative API.
Let's really contrast that, because I think a lot of us grew up writing bash scripts or using tools like Ansible, which are imperative. Imperative is commanding. It's saying, connect to node B, download this image, and start container X.
Right. And an imperative system is incredibly fragile because if node B crashes 5 minutes later, your imperative script has already finished running. It reported success and exited, the container is gone, and the system has no idea it's supposed to do anything about it.
But a declarative instruction, on the other hand, doesn't give steps. It declares an invariant reality. It says, I don't care how you do it, but maintain 3 available replicas of this pod template at all times.
So the memory framework here is imperative commands describe a step to take. Declarative objects describe an invariant state to maintain.
And to maintain that invariant state, Kubernetes uses what we call the reconciliation loop. This is the heart of the machine. It is a continuous level-triggered loop. A controller wakes up and essentially asks 3 things. What state should exist according to the database? What state actually exists in the physical cluster right now? And what is the smallest, safest physical action I can take right now to close the gap between reality and intent?
I want to pause on the term level triggered because it is arguably the most important engineering decision in Kubernetes. Most systems we build are edge triggered.
What's the difference exactly?
Well, an edge triggered system reacts to an event like a webhook firing or a button click. If the system misses the event, maybe the network drops the packet, the event is gone forever, and the system state is permanently broken.
So how does a level-triggered system differ? I usually think of it like the thermostat in your house. The thermostat doesn't care about a historical list of temperature changes. It doesn't care that someone opened a window an hour ago.
Exactly, it only cares about right now.
Right, it only cares about the current level. The desired level is 72 degrees. The current level is 68 degrees. It turns on the heater. It constantly observes the current state.
That's a perfect analogy, so let's apply that. If you have a deployment with 3 replicas, and you manually SSH into a node and maliciously kill one of the container processes, what happens? Does the deployment controller put an order into a message queue that says, hey, someone killed a pod, make a new one?
This is a massive conceptual leap for a lot of people. No,
Hmm.
there is no reliable command queue of actions anywhere in Kubernetes. Events are just hints. The state is the truth.
Right. When you kill that process, the kubelet updates the database to say the pod has failed. An event fires, which acts as a gentle hint that wakes the deployment controller up. The controller looks at the database. It sees that the desired state is 3 replicas, but the observed state is now 2.
It doesn't know or care why there are two.
It doesn't care at all about the sequence of events that led to this moment. It just acts to close the gap by creating a new pod object.
That makes the system incredibly resilient, because if the controller itself crashes while trying to fix the problem, it's fine. When the controller reboots 5 minutes later, it doesn't need to replay a history of commands. It just looks at the state again, sees 3 desired and 2 observed, and picks up exactly where it left off.
Exactly. And to manage all this complex state, we divide the cluster architecture into 2 cooperating worlds, the decision world and the execution world.
Let's break those down mechanistically. The decision world is the control plane. This is where we have the API server. The API server is a stateless REST API. It acts as the front door, the authentication gateway, and the communication hub. Behind the API server, we have etc.
Right, etc. is the durable source of state. It's a distributed key value store, and importantly, it uses the Raft consensus algorithm.
We really need to explain why Raft is necessary. Like, why can't we just use a standard Postgres database for the control plane?
Because the control plane needs to be highly available. You usually run 3 or 5 control plane nodes. But in a distributed system, you can suffer a network partition, a split brain, where half the nodes can't talk to the other half. If they both start making independent decisions about state, the cluster destroys itself.
So how does Raft prevent that?
Raft solves this by requiring a quorum. If you have 3 etc. nodes, a leader is elected. Any write, like storing a new pod, must be acknowledged and written to disk by at least 2 out of the 3 nodes before etc. tells the API server the write was successful.
Oh, wow.
Yeah. If a network partition isolates a node, it loses quorum and cannot accept writes. This guarantees the control plane always agrees on a single version of the truth.
That is brilliant. So we have the API server and etc. We also have the scheduler, which runs complex algorithms to make placement decisions. And the controller manager, which is basically a single binary that bundles together all these continuous loops we just talked about, the deployment controller, the replica set controller, the node controller.
And then across the boundary, you have the execution world, which are your worker nodes. That's where you find the kubelet, the local node level reconciler we mentioned earlier.
Yeah.
You have the container runtime chain. And you have the data plane, which is usually kubeproxy or a CNI plugin, which handles the actual packet level networking.
Now, here's a key architectural boundary. And it's a rule that completely blew my mind when I first realized the implications. Do all these controllers, the scheduler, the kubelet, the controller manager, do they all just connect directly to the etc. database to read and update things?
Emphatically no. No component writes or reads directly from etc. except the API server. This is an unbreakable architectural rule. The API server is the gatekeeper, etc. is just the dumb memory.
So if the kubelet wants to update the status of a pod to say it's running, it has to send an HTTP PTCH request to the API server. If the scheduler picks a node, it can't just update the database. It sends an HTTP request to the API server.
Correct. And this ensures that every single change to the system state goes through authentication, authorization, schema validation, and admission control. It prevents any rogue component from corrupting the state. It also allows the API server to act as a centralized broadcasting hub.
How does that work?
When the API server writes to etc., it immediately turns around and broadcasts that change to any controller that is watching.
It's the ultimate bottleneck, but in a necessary protective way. So, since every single component in the cluster must talk through the API server, we really need to understand the language they are speaking before we can even think about typing kubectl apply.
Yes. We have to dive into the API machinery. This is the grammar of Kubernetes. When you look at a Kubernetes YAML manifest, you're looking at the anatomy of an object. At the top, you always see a group, a version, and a kind, often abbreviated as GVK.
For example, the APA version might be apps v1, and the kind is deployment. The API server uses this GVK to route the object to the correct internal schema for validation.
And below that header, we have the most foundational distinction in all of Kubernetes: spec versus status. If you only remember one thing about the API today, remember this.
The spec is the desired state. This is what you, the human user, or your GitOps automation tools own. You write the spec, you say, I want 3 replicas.
And the status.
The status is the observed physical reality. This field is owned by the controllers. You, the user, do not write the status. In fact, if you try to put a status block in your YAML file and apply it, the API server will literally just strip it out and ignore it. The system updates the status to tell you what it's actually managed to accomplish.
Specs says what should happen. Status reports what has happened. And wrapped around all of this is the metadata. Now, we need to do a deep dive on some of these metadata fields because they dictate how the system manages lifecycle. First pair, name versus UID. Why do we need a 36-character UUID if I already explicitly named my pod payment processor?
Because name is a human identity, but UID is an object instance identity. Imagine you have a pod named payment processor. You delete it, it's gone. 5 seconds later, your deployment pipeline runs and creates a brand new pod, also named payment processor. To a human reading the logs, that's the same name. But to the system, it is a completely new instance in time and space.
Exactly. The UID guarantees that the garbage collector and the backend controllers don't get confused. If an old volume detachment routine is delayed and it finally wakes up, you don't want it to detach the disk from the new payment processor pod just because they share a name. It checks the UID. If the UID doesn't match, it drops the operation.
That makes total sense.
Yeah.
Okay, what about generation versus resource version? I see these in the metadata all the time.
The generation is an integer that increments whenever the desired state, the spec, changes. It tracks revisions to your intent. But resource version is an opaque storage token used by etc. and the API server to track any change to the object in the database, including status updates. Every single time the object is touched, the resource version changes.
Okay, we will come back to resource version in a second because it powers a massive feature. But last, metadata pair. Labels versus annotations.
The source material is very strict about this distinction. Labels are indexed for selection. They are key value pairs that are queryable by the API server. They are how components loosely couple to one another without knowing each other's UIDs.
So a service finds its target pods by looking for specific labels.
Right. And a replica set counts how many pods it currently owns by querying the API server for matching labels.
Annotations, on the other hand, are not indexed. They're not for selecting or querying. They are just a place to attach non-identifying tool metadata, like a build checksum, an incident ticket number, or a git commit hash. The cluster machinery ignores annotations.
Which brings up a major production trap.
Yes. The classic label disaster. I have seen this happen. An engineering team decides they want to organize their applications better. They notice a pod has a label app.backend. They decide, let's be more specific, and they run a command to change that label on the live pod to app.database. They think they are just updating documentation. What actually happens?
They instantly sever the application from the network.
Just like that.
Yep. Labels are API contracts. The moment that label changes to app.database, the service that was routing traffic to app backend runs its query, doesn't see the pod anymore, and removes it from the load balancer. The network policy that allowed traffic might drop it. You can instantly take down production just by tweaking a label you thought was only for human organization.
Ouch. Treat labels as load-bearing infrastructure. Okay, let's circle back to resource version. If the API server is horizontally scaled, meaning you have 3 API servers sitting behind a load balancer, and you have hundreds of controllers constantly reading and updating the status of thousands of objects, how do things not just get blindly overwritten? What if the scheduler and the kubelet try to update the same pod at the exact same millisecond?
Kubernetes solves this distributed systems problem using optimistic concurrency. This relies entirely on that resource version field. Unlike a traditional SQL database that uses pessimistic locking where it locks the row, makes the change, and unlocks it, Kubernetes doesn't lock anything. The pattern is read, compare, write, retry. This is often called a compare and swap operation.
Walk me through the exact HTTP mechanism of that.
When a client, like a controller, wants to update an object, it first does a getChat request. It reads the current state and notes the resource version. Let's say it's version 100. It makes its logical changes locally in memory. Then, it sends a POT request back to the API server. Inside the payload, it includes that original resource version, 100. The API server looks at the request, then looks at etc. It says, update this object, but only if the current version in the database is still 100.
And what if another controller snuck in and updated it to version 101 while you were doing your math?
The API server will reject your request with an HTTP 409 conflict error. It completely refuses the write.
And so what does the controller do?
The controller catches that error, backs off, does a new getGT request to fetch version 101, applies its math to the new state, and tries again.
That is brilliant. It ensures no one overwrites someone else's work blindly without needing expensive database locks. And to avoid overwhelming the API server with constant GET requests, controllers don't actually poll, they use watches. They establish a long-lived HTTP connection to the API server and say, stream every event to me using chunked transfer encoding. The controller keeps a local cache in memory. If it needs to make a decision, it reads from its local cache, which is lightning fast.
And if the network connection drops and the watch is severed, the controller doesn't panic. It just reconnects, asks for a list of everything to resync its cache, and starts watching from the last resource version it remembers. State is truth.
Okay, we have our building blocks. We understand namespaces, tree groups, control loops, the API gatekeeper, raft consensus, and the language of state. It is time to follow our central storyline. You are sitting at your terminal, you have your deployment.yaml file. You hit enter on kubectl apply-f deployment.yaml. What is the very first physical thing that happens?
The journey begins with the first 3 stages of our apply flow: read, resolve, and request. This all happens strictly on your laptop inside the kubectl binary. It hasn't even touched the network yet. First, kubectl reads your YAML file from disk and parses it into memory.
And then it has to figure out what to do with it. Stage 2 is resolve.
Right. It looks at your .kubeconfig file to see which cluster context you are currently targeting. It finds the IP address and the client certificates. Then it uses a mechanism called API discovery. It looks at the GVK in your file, say, group apps, version v1, kind deployment. It reaches out to the API server's discovery endpoints, like episaps v1, and asks, what is the exact REST URL endpoint for this resource?
And kubectl caches these discovery schemas locally on your laptop in a hidden folder, so it doesn't have to ask every single time.
Yeah.
This actually leads to a great troubleshooting point. If you run apply and get a weird error that says resource not found, it doesn't mean your YAML has a typo in the field. It means the cluster literally doesn't know about that API version.
Right. Maybe you're targeting a cluster running an outdated version of Kubernetes that deprecated that API.
Or you forgot to install the custom resource definition. You can verify this by running kubectl ob resources to see exactly what the cluster currently understands.
Exactly. Once it discovers the correct URL endpoint, stage 3 is the request. Kubectl serializes your intent into a JSON payload, builds an authenticated HTTPS request, and fires it over the network to the API server.
So now the packet hits the API server. We enter stages 4 and 5, which are all about rights, authentication, and authorization.
Authentication happens first. This phase simply asks, who are you? The API server runs the request through a chain of authenticators. It might check if you provided a valid X.509 client certificate. If not, it checks for an OIDC token, like an Azure AD or Google token.
And if it's valid?
If valid, the authenticator extracts a username and group memberships. It packages this into a user info object. It has successfully named the actor, but authentication does not grant you any permissions whatsoever. It just proves you are who you say you are.
All right, for permissions, we move to authorization. This asks, may you do this? And in Kubernetes, this is universally handled by RBAC, role-based access control.
Correct. The API server takes your user info object, looks at the HTTP verb you're trying to use, in this case post or petch, and the resource you are targeting deployments in the app's API group. It then queries, etc., for any role bindings or cluster role bindings that associate your user or group with a role that allows that action.
And importantly, Kubernetes authorization is radically denied by default. There are no explicit deny rules in standard RBAC. You can't write a rule that says Bob cannot delete pods. If there isn't a rule explicitly affirmatively allowing Bob to do it, Bob is denied with an HTTP 403 forbidden.
If you ever want to test this without actually deploying or breaking things, you can use a built-in command. Kubectl auth can I create deployments.apps. The API server will evaluate your RBAC and literally return a simple yes or no.
That is incredibly handy for debugging CI/CD pipeline service accounts. Okay, so we've been authenticated and our RBAC allows the action. Now the request moves into the deeply complex inner workings of the API server for stages 6 through 9, decoding, validation, and admission. These are the rules of the cluster.
First, The API server decodes the JSON payload into its own internal Go language representation. Then it passes it through admission control. This is a massive feature. Admission controllers are pieces of code that intercept the request after it's authorized, but before it is saved to the database. There are two distinct phases here: mutating admission and validating admission.
Let's look at mutating admission first. This means the cluster can actually alter my YAML payload before it saves it.
Yes, the API server can call out to mutating webhooks over the network. These webhooks receive your proposed deployment, examine it, and return a patch. They might inject default resource limits if you forgot them. They might automatically attach an Envoy sidecar container to your pod for a service mesh. They mutate the intent.
But wait, let's explore a huge production trap here. If a mutating webhook changes my YAML before it saves it to etc., my original file on my laptop, or my manifest stored in my Git repository, is now structurally out of sync with what the cluster actually stored. What happens if I'm using a GitOps tool like Argo CD or Flux?
This is a classic infinite loop scenario. Your GitOps tool reads Git and says, there is no sidecar. It pushes to the cluster, the mutating webhook intercepts it and adds a sidecar. It saves to etc. 5 seconds later, the GitOps tool looks at the cluster, sees a sidecar that isn't in Git, assumes someone made an unauthorized manual change, and tries to delete the sidecar by pushing again.
And then the webhook adds it back.
Yes, they fight forever, burning CPU.
So how do you fix it? Or even know what actually happened?
You have to configure your GitOps tool to ignore certain injected fields. And to see what the cluster actually admitted and saved, you never rely on your local file. You must run kubectl get deployment your app YAML. That shows you the live mutated object as it exists in etc.
Okay, wow. So after the payload potentially gets mutated, we hit validating admission.
Right. This is the final unyielding gatekeeper. Validating webhooks or CEL common expression language policies inspect the final proposed object and can outright reject it. They enforce corporate governance. They might say, no, you cannot run this container as root, or no, you must pull this image from our internal secure registry, not Docker Hub. If the payload fails validation, the API server drops the request and sends a detailed error message back to your terminal.
Assuming we pass validation, we arrive at stage 10, server-side apply, and field ownership.
This is a newer mechanism. Historically, kubectl tried to calculate a three-way diff on your laptop. Modern Kubernetes uses server-side apply. The API server takes over the merging logic. It uses a system called managed fields. It meticulously tracks which specific actor, which tool or user owns which specific line item in the YAML.
So if my GitOps tool manages the image field, but a horizontal pod autoscaler is constantly running in the cluster and updating the replicas field based on CPU usage, they won't overwrite each other.
Exactly. They negotiate ownership dynamically. If you try to manually apply a change to the replicas field that the autoscaler currently owns, the API server will throw a conflict and say, hey, another field manager owns this. You either have to back off or explicitly pass a force flag to intentionally steal ownership.
Okay, we've navigated the gauntlet. We reach stage 11, persist.
The API server finally serializes the validated, admitted, and merged object back into JSON and commits it to etc. Because etc. uses Raft consensus, it ensures that write is durable, synced to disk, and ordered. Once etc. confirms the write, the API server sends an HTTP 200 OK response back to your kubectl client.
And on my terminal screen, I see deployment.app checkout configured, the big green check mark. I did it. But here is the massive aha moment of this entire deep dive. If I immediately run kubectl get pods right after I see that success message, they are not there. I have 0 pods. Why? Didn't the API server just say it was configured?
It did say configured, but we need to return to our foundational memory framework. Accepted is not scheduled. Scheduled is not started. Started is not ready. Ready is not reachable. All kubectl apply did was confirm that your intent was successfully validated and stored in, etc. That is it. At this exact millisecond, no physical pod is required to exist anywhere in the universe. The API only recorded the request. Now, the execution world must react to that new intent.
The intent is locked in the database. Now the watchers wake up. Welcome to Section 5, Controller Cascades and Ownership.
Right. Because the API server just wrote a new deployment to etc., it publishes a watch event over those long-lived connections. The deployment controller, which is a loop running inside the kube controller manager binary, receives this event.
It wakes up and says, aha, a new deployment intent. I need to make sure this happens. And in stage 12 and 13, it starts doing the math. It looks at the pod template inside your deployment. It calculates a cryptographic hash of that template. And then it creates an entirely new object in the API server called a replica set. Wait, let's stop here. Why? Why does a deployment need a middleman? Why does the deployment controller just read the intent and make the pods directly?
Rollouts.
Mm.
The entire reason deployments exist is to manage stateful transitions. If you change the container image version in your deployment, the controller calculates a new hash for the new template, and it creates a brand new replica set alongside the old one. Now you have two replica sets. The deployment controller manages a mathematical dance. It slowly scales the old replica set down by 1 while scaling the new replica set up by 1. This is how you get zero downtime rolling updates. The deployment manages the rollout strategy. The replica set handles the actual template stamping.
Oh, that makes so much sense. It abstracts the versioning. So the deployment creates the replica set. Now, the replica set controller's watch fires. It wakes up, sees it desires 3 replicas according to its spec, but it currently has 0 in its status. So it sends an API request to create 3 actual pod objects.
Exactly. It's a cascade of intent. And because the system is generating all these downstream child objects, it needs a mechanistic way to keep track of them for lifecycle management. It uses a metadata field called owner references.
Let's detour into ownership and deletion for a second, because this is how garbage collection works. When the replica set creates the pods, it links them by injecting its own UID into the pod's owner references array. So if I eventually delete the top-level deployment, how does the system know to clean up the replica sets in the pods? Does it happen instantly, like a cascading delete in a SQL database?
No. It relies on asynchronous garbage collection and finalizers. When you request a deletion of the deployment, the API server doesn't just wipe the row from the database, it slaps a deletion timestamp on the object.
So a deletion timestamp simply means wanted gone. It's marked for death.
Yes. And the garbage collector controller sees this, follows the owner references down the tree, and puts a deletion timestamp on the replica sets and then on the pods. But there is a catch. If any of these objects have a finalizer string listed in their metadata, it acts as a hard lock. A finalizer means cleanup, not yet proven.
What kind of cleanup, though?
Well, imagine a service object that provisioned an Amazon Web Services elastic load balancer. If you just delete the object from the database instantly, the AWS cloud resource is orphaned. You'll pay for it forever. So the controller puts a finalizer on it. When you delete it, it gets a deletion timestamp, but the API server refuses to remove it from etc.
So it waits.
Right. The controller notices the timestamp, reaches out to the AWS API, physically deletes the cloud load balancer, and then the controller sends a patch to remove its finalizer string. Only when the finalizer's array is completely empty will the API server actually delete the object from etc.
This is critical for troubleshooting. I have seen developers get so frustrated when an object is stuck in a terminating state for 20 minutes. They try to run kubectl delete force. But if it's stuck, you don't just forcefully edit the database to remove the finalizer. You look at the finalizers list to see which controller is failing to do its physical cleanup. If you bypass it, you leave orphaned resources.
Exactly. Don't fight the finalizers. Fix the underlying controller that's stuck.
Okay, back to our storyline. The replica set controller has successfully created 3 pod objects in the API server. They are saved in, etc. But if we look at them, their spec.nodename field is completely empty. They exist as durable scheduling requests, but they don't have a home. No node knows they exist. We need the scheduler.
Welcome to stage 15, solving the placement puzzle. The kube scheduler is an independent binary. It is constantly watching the API server for any pod that does not have a node name assigned. When it sees our 3 new pods, it puts them in a scheduling queue. It takes one off the queue and runs a highly complex scheduling cycle. Filter, score, and bind.
Let's walk through the mechanisms of that. First is the filter phase. This is looking for hard constraints, right?
Yeah.
It's binary.
Yes. It takes the list of every single node in the cluster and ruthlessly filters out any node that cannot possibly run the pod. Does the pod require a specific node label, like disk typed? Eliminate the nodes that don't match? Is the node tainted with a no schedule taint and the pod lacks a toleration? Eliminate it.
And the biggest constraint, resources. I had to show a classic developer complaint here, a major host trap. A developer comes to me and says, I have a node in my cluster that is sitting at 0% CPU usage. It's totally idle. But the scheduler refuses to put my pending pod on it. Why is Kubernetes broken?
Kubernetes isn't broken, their mental model is. This is a fundamental, non-negotiable rule of Kubernetes scheduling. Requests reserve, limits restrain, usage reveals. The scheduler does not care about live physical CPU utilization. It doesn't query the node to see how busy it is. It looks entirely at requests, which are declared mathematical reservations.
Let's break that down with math.
Sure. If you have a node with 8 physical CPUs, you have 4 pods running on it, and each pod requested 2 CPUs in its YAML manifest. That is a total of 8 requested CPUs. That node is 100% fully reserved. It does not matter if those 4 pods are currently idle and using 0% of the CPU physically. The capacity is spoken for. When the scheduler evaluates that node during the filter phase, the math says 8 minus 8 is 0. There is no room. It filters the node out.
Request reserve. The scheduler is an accountant, not a performance monitor. Okay, so after the filter phase, we have a smaller list of feasible nodes. Then we move to the score phase. These are soft preferences.
Right. It runs a series of scoring plugins to rank the remaining nodes from 0 to 100. Does one node already have the container image cached on disk? Give it points. Do you have a topology spread constraint asking to balance pods across availability zones? Score nodes higher if they are in an empty zone. The scheduler tallies the score and picks the winner.
Before we bind, let's quickly review taints, tolerations, and affinity, because these dictate filtering and scoring.
Yes. A taint is applied to a node. It acts as a repellent. It says keep out. A toleration is applied to a pod. It acts as a bypass key. It says I may enter that tainted node. But an affinity rule on a pod is an attraction. It says I want to be scheduled here.
So the scheduler picks the best node based on all of this math. Now for the bind phase, the scheduler actually reaches out to the node and spins up the container.
No. Remember our unbreakable architectural rule? Only the API server writes to, etc., and control plane components do not talk directly to the execution nodes. The scheduler does not talk to the kubelet. The scheduler simply creates a specialized binding object and sends it via HTTP to the API server. This simply updates the spec.node name of the pod in the database to say node ABC. That is the only physical result of the scheduler's hard work. It updates a string.
Wow. It just writes down an address. And if the scheduler fails to find any node that passes the filter phase,
The pod just sits there, stuck in the pending state.
and to troubleshoot that, you'd use kubectl describe pod and look at the events section at the bottom. The scheduler will emit an event detailing exactly which filter blocked it, like 010 nodes are available, 3 insufficient CPU, 7 nodes, didn't match pod's node affinity.
Precisely. The events tell the story of the reconciliation failure.
Okay, so the pod has an address written in the database. Now the local foreman on that specific node has to actually wake up and build the physical house. We enter section 7. The node awakens.
Stage 16. The kubelet process running on the assigned node is constantly watching the API server, its watchfires. It sees a pod where spec.node name matches its own physical host name. It realizes, hey, this is my job now. It fetches the full pod spec, it fetches any required secrets or config maps from the API server, and it begins its local sync loop to make reality match the intent.
Stage 17 is sandbox and networking. We're getting physical now.
Finally, the kubelet talks over that gRPC container runtime interface, the CRI, and says, create a pod sandbox. The container runtime usually fulfills this by creating a tiny, hidden infrastructure container, often called the pause container.
What is the point of a pause container? It just sleeps forever.
It does sleep forever. Its entire physical purpose is just to hold the Linux namespaces open, specifically the network namespace, while other containers come and go. If you didn't have the pause container and your main application container crashed, the network namespace would be destroyed by the kernel. You lose your IP address. By having the pause container hold the namespaces, your application container can crash and restart inside the same isolated bubble without losing its network identity.
It's literally laying the foundation of the house before you build the rooms. So the sandbox is created. Now we need an IP address.
The runtime calls out to the CNI the container network interface. This is a massive ecosystem, things like Calico, Cilium, or Flannel. The CNI plugin does the heavy lifting. It creates a virtual Ethernet pair, a VETH pair. It leaves one end on the host's root network namespace and shoves the other end into the container's network namespace. It reaches out to your IP address management system to assign a pod IP, and it configures the routing tables so packets can actually flow from the host bridge into the container.
And this is a massive failure checkpoint. I see this all the time. If the CNI fails, maybe it ran out of IP addresses in the subnet, your pod gets stuck in the container creating state.
Yeah.
And developers will frantically run kubectl logs to figure out why their app isn't starting.
And what happens?
It throws an error because the application container doesn't even exist yet. You cannot get logs for a process that the kernel hasn't started. If it's second container creating, you have to check the kubelet logs on the node itself using journaling tool, or use kubectl to see why the sandbox failed.
That's a vital troubleshooting tip. But assuming the CNI successfully wires up the network, We move to stage 18, images and application
The
containers.
runtime pulls the container image.
And here we have a strong warning from the source material regarding mutable tags. If you deploy an image using the tag latest, or even a floating tag like v1, you introduce chaos. Node A might pull ubuntu.latest on Monday. A week later, Node B scales up and pulls ubuntu.latest, but the publisher updated the image on Wednesday. You now have two completely different file systems running in production, even though the YAML looks identical.
Always use image digest for production.
Hmm.
The SHA-256 hash, it's cryptographically locked. Okay, so the runtime pulls the image, unpacks the file system layers using overlays, and translates the kubelet's configuration into all those kernel groups and namespace system calls we talked about in the very beginning. The container process starts.
And this reveals the pod's true architectural nature. A pod is one address, one placement decision, one fate, but possibly many processes. Because they share that POS container's network namespace, multiple containers in the same pod can talk to each other over a local host.
Since we can have multiple containers in a single pod, what is the mechanistic difference between an init container and a sidecar container?
Init containers run strictly sequentially. Container A must start, do its job, and successfully exit with a 0 code before container B is allowed to start. And all init containers must successfully exit before the main application containers are even created. They are perfect for running a database schema migration or a script that waits for an external dependency.
But wait, don't use them to wait forever for a database to come online, right? If your init container runs an infinite loop waiting for a DB, your pod is just permanently stuck initializing.
Exactly. Native sidecars, on the other hand, use init container semantics for startup. They start before the main app, but they stay running constantly. They don't exit. They run alongside the main application. This is how you run a logging proxy or a service mesh envoy proxy that needs to be active before the main app sends any traffic.
Okay, what happens if my main application container just crashes immediately upon startup? Say, it's missing a required configuration file.
The kubelet, which is monitoring the process via the CRI, will notice the process exited with a non-zero code. Based on the pod's restart policy, the kubelet will ask the runtime to restart the container inside the existing sandbox. But if it keeps crashing immediately, over and over, you will see a status of crash loop backoff.
I have seen that status 1,000 times.
It's important to understand that crash loop backoff is a backoff condition, not an execution phase. The kubelet is applying an exponential backoff algorithm. It waits 10 seconds, then 20, then 40, up to 5 minutes between restart attempts. It does this to protect the node's CPU and disk from being overwhelmed by a tight restart storm.
So it's protecting the physical hardware. Okay, let's say the configuration is fixed. The process is finally running without crashing. But just because a process is alive and taking up memory doesn't mean it's actually ready to do its job. A Java app might take 40 seconds to warm up its caches. We are at section 8, probes, status, and traffic.
Stage 19. Kubernetes needs to know the logical health of your application, not just the OS-level process state. It uses 3 types of probes. The mechanistic framework here is: startup asks, have you begun? Readiness asks, should you receive network traffic? Liveness asks, should you be restarted?
Let's focus deeply on readiness and liveness because people mix the physical mechanisms of these up constantly. What actually happens if a readiness probe fails? Say, my HTTP endpoint returns a 503. Does the kubelet kill the container and restart it?
No. If a readiness probe fails, it simply means the application is busy processing a heavy batch job, or warming up a cache, or temporarily disconnected from its back-end database. The system just marks the container's readiness condition as false. The physical effect is that it removes the pod's IP address from the list of available endpoints. Network traffic stops flowing to it. But the Linux process is left entirely alone to recover on its own.
But if a liveness probe fails, that means the system thinks your app is completely deadlocked. It's stuck in an infinite loop and will never recover on its own. Then the kubelet will send a sigterm, and eventually a sigkill, to terminate and restart the container.
Precisely. Liveness modifies the process state. Readiness modifies the network routing state.
Okay, let's say our readiness probe passes. We hit stage 20, endpoint slices, and reachability.
Once the readiness condition is true and etc., another controller, the endpoint slice controller, sees this state change. It takes the pod's IP address and adds it to an endpoint slice object that is associated with your service.
And then the data plane finally takes over.
Right. On every single node in the cluster, a daemon called kubeproxy, or perhaps your CNI's eBPF data plane, is watching those endpoint slices. When it sees your new pod IP added to the slice, it reaches down into the Linux kernel and programs the forwarding rules.
Let's explain how it programs the kernel, because it's fascinating. Historically, kubeproxy used iptables. It would write a massive list of sequential rules. But that creates an ON linear search problem. If you have 5,000 services, every packet has to evaluate 5,000 rules to find its destination, which creates terrible latency. Modern clusters use IPVS or eBPF.
Oh, eBPF is a game changer.
It is. eBPF allows Kubernetes to inject compiled programs directly into the kernel's networking stack using O1 hash maps. It routes the packet instantly.
Exactly. So when a user hits the service IP, the kernel intercepts it, looks at the eBPF map, and knows to rewrite the destination IP and forward that packet directly to our new pod's specific IP address.
But I have one more host trap here, the ultimate final boss of developer headaches. Let's say you've done everything right. My application process is running. My readiness probe passes locally, the eBPF maps are programmed, but when I try to send traffic through the Kubernetes service from another pod, I get connection refused. Why?
9 times out of 10, we have to look at the application code itself. The developer configured their web server to bind to localhost or 127.0.1 inside the container. That means the application is telling the kernel, only accept traffic originating from inside my own private network namespace. To receive traffic from the outside world through the Kubernetes service, the application code must bind to 0.0.0 or the specific IP of the pod's F0 network interface.
Because from the application's perspective, the service traffic is coming from a foreign IP address outside its private little world.
Exactly. But if the application is bound correctly to 0.0.0, the packet finally flows. The declarative intent you typed into kubectl apply has become physical reality.
We made it. From a YAML file parts on a laptop, through cryptographic consensus, through scheduler algorithms, down to a CNI virtual Ethernet cable, and finally a packet hitting a running Linux process. That is an incredible journey.
It is arguably one of the most beautiful pieces of distributed systems engineering we have today.
Let's bring it all home with our outro. We need to do a rapid-fire verbal replay of this journey. For everyone listening, if you can memorize these 9 R's, you will always possess the mental model to know where you are in the Kubernetes lifecycle.
Here we go. Read. Kubectl parses your YAML from disk.
Resolve. It queries discovery to find the correct API endpoint.
Request. It sends the authenticated HTTPS payload.
Recognize. The API server decodes and schemas the resource.
Writes. Authentication and RBAC authorization evaluate who you are and what you can do.
Rules. Admission webhooks mutate the payload or reject it entirely.
Record. The API server persists the final object into etc. via raft.
Reconcile. Controllers like the deployment and replica set react to the intent and create child objects.
And run. The scheduler binds, the kubelet fetches, the CNI wires, the runtime starts, and the application becomes ready.
Read, resolve, request, recognize rights, rules, record, reconcile, run.
I love it. And if things go wrong anywhere along that physical path, we have the scope troubleshooting framework. Start with a symptom. Compare intent versus reality. Observe the evidence using describe and events. Pinpoint the physical owning component. Is it the scheduler, the kubelet, a controller? And finally, explain the failed transition. And remember the golden rule of troubleshooting. Always check kubectl get events and look at the conditions array in the status before you blindly check kubectl logs. Because as we've learned, if the network failed to attach or the image failed to pull, the container process doesn't exist and the logs don't exist. You will be chasing a ghost. Look at the state first.
Before we sign off, I want to leave you with one final, deeply provocative thought to mull over. We just spent this entire deep dive walking through how a standard built-in deployment creates a pod. But what happens if you install a third-party extension? What if you apply a custom resource definition, a CRD, for a complex Postgres database operator?
This is the genius of the entire system architecture. The exact same machinery applies. The HTTP watches, the REST API mapping, the optimistic concurrency loops, the RBAC, the admission webhooks, the managed fields, it's functionally identical. The API server does not care if it's a built-in deployment or a custom Postgres database object. It's just a schema in etc.
If you deeply understand this one mechanistic journey we took today, you literally understand how to extend Kubernetes to control anything in your infrastructure. You can write a controller to manage DNS records, AWS S3 buckets, or even order pizza.
It's all just intent, observation, and closing the gap.
Thank you so much for taking this microscopic deep dive with us. You now have the mental debugger to look at any unfamiliar object, skip the blind memorization, and ask those crucial mechanistic questions. Remember, it's not a vending machine. It is a highly coordinated team constantly reading a bulletin board, working relentlessly to build your house. See you next time.